Hi, good day. My name is Janelle Zamore. I work in the Office of Advanced Reactor Technologies within the Office of Nuclear Energy, and I am the federal point of contact for this IRP. The technical point of contact is Dr. David Holcomb at the Oak Ridge National Lab. And today I'm going to give a brief overview of the proposed IRP to tackle integrated approach to fluoride high temperature reactor technology and design challenges. Move into the second slide. So why is the Office of Nuclear Energy interested in FHRs? FHRs have the potential to support both base load and peak electricity production. Due to their high operating temperatures, they have the potential to expand the use of nuclear energy beyond just electricity generation into process heat applications. And this expansion of nuclear energy into process heat can potentially reduce greenhouse gas emissions as well as increase energy security. FHRs can provide improved thermal efficiencies up to 45% compared to 33% for light water reactors. They also feature full passive safety, and they do not require any active system or operator action to avoid large off-site releases during accident scenarios. Their high operating temperatures increase compatibility with dry cooling, which is becoming increasingly important worldwide. Although FHRs have some similarities to MSRs, they use a solid fuel form instead of fuel dissolved in liquid salt, alleviating some of the design challenges. However, although they are very promising concepts, there are some remaining challenges which need to be overcome. And this will be the topic for the IRP. Some technical challenges include advanced materials, tritium management, instrumentation, redox control, and we'll go through these on subsequent slides. These challenges were derived based on output from the FY11 IRP, a technology development roadmap that was developed at the Oak Ridge National Lab, as well as historical data based on operation of MSRs. Moving to the third slide. Due to the high operating temperatures, as well as the liquid salt environment, finding suitable materials can pose a challenge. Continuous fiber composites, or CFCs, have the potential to enable improved high temperature reactor performance. FHRs can make extensive use of CFCs for reactor vessel internal components. Some of these components will be large and have complex geometries, so R&D is needed to develop the composite architecture and fabrication methods for large structures, as well as the associated design rules. Quality assurance, codes and standards, performance and cost data is also needed. In terms of metals, alloy N and 316 stainless steel are two existing alloys currently under consideration. Alloy N has a very high corrosion and oxidation resistance, but it has a lower high temperature strength compared to other advanced alloys. Alloy N is not currently approved as a material for high temperature reactor use, and a materials qualification effort will be required to use alloy N in FHRs. In terms of 316 stainless, although it does have an approved code case, design data is needed for corrosion considerations and compatibility with liquid salt. In addition to these existing alloys, development of improved salt-compatible alloys will be beneficial. Any proposed improved material will of course need to go through a qualification process. Clad structures are another alternative for use in FHRs, and development of rules for clad structures are needed, and fabrication issues need to be evaluated. Finally, R&D to examine chemical compatibility of both the structural and functional materials with liquid salt is needed. Going to the fourth slide. Tritium management is an issue in FHRs. Tritium capture in FHRs is complicated because at high temperatures, tritium permeates through available structural alloys. Research is needed on methods and technologies to prevent tritium release. Some options to consider include chemical traps, separation methods for molten salts, and tritium barriers. High temperature fluoride salts will dissolve oxide protective layers on structural alloys. Development of primary coolant redox control systems are needed. Technologies to remove small amounts of fission products and dissolved fuel from the liquid salts are desired. Finally, instrumentation for liquid salt reactors need to be addressed, and techniques that overcome some of the implementation challenges are encouraged. Moving to the fifth slide. Design, testing, and life cycle analysis for salt heat exchangers are needed. Neutronic and hydraulic design codes need benchmarking and validation for use in licensing. FHRs also present unique design and operational challenges due to the liquid salt environment. For example, salt-compatible valves and advanced pumps are needed. Testing of materials and components under prototypical conditions will reduce uncertainty. And let me just point out here that the list of challenges that I just went through are not meant to be all-encompassing. So other design challenges that are proposed will be considered. And of course, these challenges will be weighed based on technical merit and programmatic requirements. Moving to the sixth slide. So some of you may be wondering, how does this compare to the FY11 FHR IRP, which is currently ongoing? The FY11 IRP was more focused on the big picture of a commercialization path for FHRs, including a test reactor design, a power reactor design, and a licensing strategy. There was also some supporting R&D performed in the area of thermohydraulics and materials testing. But this proposed FY14 IRP is more focused on an integrated approach to solving some of the remaining technology challenges. Moving to slide 7. Some key points on the proposal for FY14. R&D proposed must support salt-cooled, solid-fueled, high-temperature reactor concepts. Work scopes that propose fuel qualification or fuel dissolved in liquid salt will not be considered. Work scopes that propose to design an FHR will not be considered. Since one of the goals of the NEOP program is knowledge management and retention, teams must include multiple universities so that the expertise in this concept can be cultivated at multiple institutions. Teams must propose an integrated approach to solving 2 or more technology challenges associated with FHRs. Favorable consideration will be given to proposals having a potential impact on other reactor concepts and even other energy sources such as solar. Proposals should clearly indicate these identified impacts. Also, applicants should identify how proposed R&D will aid in the future deployment of FHRs. Moving to the last slide, proposals should also cover what's detailed on this slide. One key thing to point out is that the proposals need to show how they will build upon work that was previously done on salt-cooled reactors, as well as how the work they propose will be different from the work done on salt reactors. And to that end, we plan to post all the documents generated under the FY11 FHR IRP will be posted on the neop.gov website, and also the technology development roadmap being developed at Oak Ridge will be posted so that applicants can compare their proposals to what was done under the 11 IRP. And with that, I can take any questions.
David, are you there?
Yes, I'm here. I believe Janelle gave an appropriate overview of the goals and the intent of the IRP. I'm available if someone has technical questions.
Okay, the first question is, to what degree should this proposal maintain a wide range of FHR design options versus looking at one of the more specific design concepts?
There are a few design concepts out there, such as the AHTR design concept that can be considered, but some of the basic characteristics, such as 700 degrees C and liquid salt environment, should be broadly considered.
Can you explain more on how carbon fiber composites are needed? What type of research is encouraged? Modeling or optimization? I'm
going to pass that question to David Holcomb.
Carbon fiber composites are especially useful for in-core structural elements. They give a slightly better moderation than a silicon carbide fiber elements. So, for example, fuel assembly supports, would be a useful thing to make with a carbon fiber composite. For things which are near to the core but are not as important for moderation, things like upper and lower core support plates, fuels, and top and bottom support structures, perhaps the silicon fiber composites would be more appropriate.